Greetings, everyone. My name is Sheshadri KR. I'm a third year PhD student in Cloud Systems Lab, Indian Institute of Science. I'm currently being advised by J. Lakshmi. In this talk, we'll be discussing our ideas on QoS Aware FaaS platform. The talk is structured as follows. So we'll be looking at the introduction of the area of function as a service. Then we'll be looking at why even QoS is needed in FaaS, and expectations for a QoS aware FaaS platform, and some experiments to back our ideas. And I'll summarize the work and highlight certain future directions to take. To begin with, there are a lot of different cloud computing services which are offered, such as infrastructure as a service, container as a service, platform as a service, function as a service, and so on. The degree of abstraction of each of these computing service varies. So for in IaaS, the abstraction is the lowest, as it gives the notion of a complete bare machine, whereas in function as service it offers functions as a basic unit of service. Similarly, when the amount of abstraction is high, the management for the user is less, as he is just concerned about using the service, and function as a service is the easiest to manage. So FaaS is a form of serverless computing. The platform automatically provisions, manages, and administers servers. It offers ease of use because the platform provider automatically manages the servers. Enhanced quickness of development. Adding new functions to an application is easy, or replacing an existing function is easy. It offers elasticity. It is highly responsive to changing workloads of the application. More importantly, it brings in a powerful pay-as-you-go billing model, where the cost is computed based on the amount of time a code is executed. This is a stark departure from the existing services, where the cost is priced based on the amount of time a resource is reserved. So let's take an example. Consider a function x which executes for 10 seconds, and the resource associated for it is 1 GB, and the cost of executing for 1 second of 1 GB of resource instance is $1.5. So the total cost of executing it is $15. So let's look where the FaaS computing service falls as far as cost perspective is concerned. So we consider an illustrative example, which is a single function which executes for 1 second, and the resource associated with it is 1 GB. So we take three scenarios to show where it actually fits and where it does not. In the first scenario, there is a 60-minute, all three scenarios there is a 60-minute window. In first scenario, 60 requests can occur at any point of time. In second, there's 5,000 requests which arise uniformly. In the third, the 13,500 requests are of execution for that function arrives uniformly. So you can see that when the number of requests are less and it is sporadic, FaaS does well. Whereas in scenario 2 and scenario 3, there is a uniform amount of request, and the allocation of resources can be properly done and it can be maximized. Hence, FaaS is not cost effective in these two scenarios. And the cost pricing for the concerned pricing for calculating these numbers were taken from the AWS pricing for various cloud computing services. So FaaS offers certain key attributes for functions. So the function should be stateless, which means between executions it cannot save state. An external database is usually used to save such states. It is event driven, which is usually invoked by a HTTP request or completion of one function or something like that. It should complete in short duration. There are certain limits on how long a function can execute, and existing platforms have certain constraints for these functions as well, such as limitations on the size of memory a function can have, timeout for stopping, maximum size of input, and the code itself. So in the contemporary literature, microservices are the provisioning constructs for FaaS, and they can be deployed as processes within containers or processes on bare metal machines. And Usually there are two types of microservices. One is persistent and the other is temporary. The persistent microservice, it needs to be present at all time. For example, a web service which keeps receiving incoming requests from clients. So these kind of services are well suited to be hosted in IaaS type of computing service. There are some other services such as temporary microservices which are invoked only on need basis. For example, authentication of a user when a login request is made. So this can only be invoked when such a request arises. These kind of services are well suited for FaaS. So now let's look at various application domains which have adopted FaaS widely, and we derive certain application requirements from them. So we can cluster the application domains into three pockets. One is the web applications, the other is analytics and IoT, and the other is network security. In web applications, e-commerce applications and certain back-end services of web applications are used to host and function as a service. Here we can see varying service requirements based on the time of the day, or the amount of time a particular service has to take to finish. It can vary based on the type of customer the service the request is coming from, and only certain services may need to be scaled. Such kind of various requirements can come from web applications. In analytics and IoT, analytics in the ML services are usually a part of certain applications, application pipelines, and part of the application pipelines can be used as the used as ML service and are implemented in FaaS. So here also the requirements can vary based on the size of the image, the type of model. So the CPU and the GPU cores for that particular service can vary based on these factors. Coming to the IoT domain, there's a heterogeneous spread of computing resources which goes from edge, fog, and cloud. It can the similar ML services can themselves be a part of can themselves be a part and executed in one of these computing spectrum, or it can be and it can have certain low latency requirements, and since it's the battery, it's a constrained environment for the battery. There can be demand on the amount of the type of compute which is done on the computing resources, and even execution preference can be a requirement when we are talking about IoT. Insofar as network security is concerned, authentication of a service, spam filtering, anomaly detection, all these services have varied requirements themselves, and these are all event driven. For example, spam filtering can be activated when certain new type of new pattern of packets are entered into a network. Other than that, network virtual functions are another good fit for FaaS. They constitute service function chains, and the requirements can vary based on the amount of network traffic which goes through the network. Some of the good examples are firewalls and intrusion detection systems and so on. So each of these application domains display characteristics which are a good fit for FaaS. In order to enforce these requirements, QoS specification is needed. The QoS framework should be flexible and general enough to accommodate requirements from varying domains. QoS for FaaS must be application centric and must have declarative features which can be interpreted by the platform for necessary implementation. Let's look at some of the sample QoS inputs that we can get from all these domains. Input size is one such parameter where the size of the input can be specified in a numeric as a number or an integer, and timestamp is another such thing. Execution preference is another such thing. In case of IoT domain, the execution preference can be edge, fog, or cloud, and the number of packets themselves can be entering a particular service can be a QoS input. Based on that, certain resources and so on can be allocated for that particular function. Let's take a look at the cost plot for a face detection function, which highlights what is missing in the existing platform. For that, we consider a single function, which is face detection. It takes an image as input, performs face detection using gasket classifier, and writes the recognized faces to the database. This function can get two input images sizes, two input sizes. One is 5 MB image, the other is 10 MB image. So if given this scenario, we have to now identify and the function has to finish within a QoS metric of 8.5 seconds. Given this scenario, we now have to find the correct resource for this function, which makes the function execute within 8.5 seconds for all the input. Now let's look at the plots here. The x-axis indicates the number of vCPUs assigned for a function. The y1 axis indicates the time taken for the function to finish. The y2 axis denotes the cost incurred for executing that function. Given this, we can see that when the number of vCPUs is 2, the function can execute within 8.5 seconds for all the image sizes. However, we can also observe that the same can be achieved when the number of vCPUs is 1 and the image size is 5 MB. This means every execution of a 5 MB image with 2 vCPU is incurring extra cost. You can make two observations from this. QoS specification is needed to express such flexible requirements. The existing platforms cannot accommodate the variety in specifying application requirements. With QoS specification, it can lead to cost beneficial executions, and existing platforms cannot satisfy such a requirement. And not just that, there is a need of QoS aware resource manager, which binds such type of QoS requirements which functions with function instances and performs the best resource mapping based on the available resources and so on, and that leads to cost efficient way of executing the function. So one way of telling the application requirements is using QoS specification. So let's take an example. The equation 1 indicates a sample QoS specification. QoS of AJFI of x indicates that the function fi should be executed with resource instance R1, resource scheme R1, if the size of the image is between 5 MB and 500 KB, and it should be executed with resource scheme R2 if it is between 5 MB and 10 MB. And the resource scheme themselves can be independently defined using a resource scheme file. Here R1 is having 1 vCPU and 1 GB RAM. This can be resource scheme can be naturally extended to include other resources such as network bandwidth and so on. So let's look at to realize these ideas. We built a prototype to show how this QoS specification can be used to achieve better executions, cost efficient executions. So this this platform consists of two main parts. One is the QoS binding engine and the QoS deployment engine. This is the only addition that we have done to the general FaaS architecture, such as Open Lambda and Open Whisk and so on. So the first, let's look at the workflow of this diagram. The user uploads the function and all the QoS specification rules associated with that function to the database. And anytime when he issues a request for that function, the extra parameter needed is the QoS input. Based on the function, the QoS binding engine will retrieve the appropriate QoS specification for that function and pass the associated resource scheme to the deployment engine. The deployment engine will will give the appropriate placement decision to the appropriate placement decision on the worker, and finally the function gets executed and the result is passed to the user. Here we have used bin packing algorithm as the load balancer in the QoS deployment engine. So basically what we are trying to achieve is, in the existing platform there is no sensitivity with respect to input for the existing platform. There is, all the input images are executed on the same resource specification, and it can lead to cost inefficient executions. In the proposed platform, we wish to bridge this gap by having this QoS specification for the user, so that the functions can be executed with their appropriate resources. Let's look at certain initial results on this platform. For the experimental setup, I highly recommend you to look at the paper. But for the first experiment, we wanted to show the cost savings that our QoS aware FaaS platform can bring in. We consider a single phase detection application which uses cascade classifier. The workload for this is a trace which we took for every 1 hour on a 24-hour period of a Azure cloud function trace, and the input image size for the function is 500 KB, 5 MB, and 10 MB, which goes along with the invocation count distribution. So the baseline for this is to run the function in a peak resource configuration, that is the configuration which deems fit for 10 MB, and the QoS metric for this is 20 seconds. So for the function, for the case of 500 KB and 5 MB image, we can see that the functions execute with lesser resource configuration compared to the peak resource configuration, and it still meets the QoS metrics deadline, and hence it results in the cost savings. Same is the case with 5 MB, but in the case of 10 MB, both non-QoS, which is the baseline, and the QoS has the peak resource configuration, and hence it does not relate to any resource cost savings. The other aspect to look at is the resource utilization at the provider, and we take the number of vCPU seconds used by a function. We show up to 34% and 39% vCPU seconds saved for 500 KB and 5 MB images. This is because we can now execute the functions with the appropriate resource size that is meant for the input size. The current QoS specification in the QoS aware FaaS platform just considers input size. There are many other parameters that can be considered. For example, timestamp is one such thing, location preference is one such thing, and the resource scheme can be naturally extended to include network bandwidth and so on. And the current specification uses simple numerical input with relational operators. Even with this setup, it achieves better resource utilization and cost savings. Apart from this, there are many other explicit and implicit parameters which affect the execution of a function. So some of the explicit factors are something which the application can declare right away in the beginning. Concurrency is one such thing, timeout is another such thing, and the resources for the function, of course, is another thing. Implicit parameters are internal factors which affect the platform. The major things are the number of cold starts and warm starts that a particular function has, and the queuing delay and resource interferences and so on. We wish to take this in a deeper study in the upcoming works. So existing platforms are insufficient in capturing wide range of application requirements, and it can lead to cost inefficient execution. And the QoS specification is proposed to address this gap, and it provides a way for the application to express the requirements. QoS requirements are derived from various application domains which have adopted FaaS, and a simple FaaS QoS aware FaaS platform prototype is developed to show the usefulness of the proposed idea. And the experiments based on real world trace show the cost savings and resource utilization achieved by the proposed ideas. So in the current setup, we have just considered a simple function. We can go ahead and consider multiple function chain workloads with diverse resource usage characteristics for each of them. Increase the support for QoS specification and support the complex operators and queries than simple relational operators. And we can increase the state space of the QoS metrics naturally can be increased to include things such as reliability of functions, power usage, and so on. And more importantly, we want to look whether this QoS specification can be deduced by the platform itself instead of being expressed. So this research will answer what class of applications can get benefited from FaaS, is QoS by itself is needed, and what are the components of such a platform and how it might look like, and so on. So I would highly encourage you to go through the work which you have done, and if there is any questions, I'll be happy to take, and you can send a mail to this ID.